I want to talk a bit about powering up LED arrays. This is a LED array that happens to be a Bridgelux 018. It's rated between 1 and 2 amperes. Takes about 30 volts. Now, some people, even the manufacturers, suggest constant current power supplies, which are okay if you have one, but some people think you can't burn out a LED if you have a constant current supply, and that's not exactly true. Let's say I gave this LED 1 ampere, which is half its rating, and I let it heat up to over 120 degrees. It would burn out. So constant current is not going to save your LED. Now, in this particular power supply, this is very simple. It's a transformer, a bridge rectifier, and a small filter capacitor. There's actually 2 supplies here. There's no regulator, no electronics. Now, I'm going to turn it on. And, woo, don't aim the LED at the camera. And we'll see it's 30 volts and it's taking 1600 or so milliamps. It's normally rated between 1 and 2 amps for that particular LED. Now, I was lucky to get this transformer, or these transformers, that are exactly the right voltage, so I don't need a regulator. And because I'm keeping that LED cool with the heatsink and the fan, I don't have to worry about thermal runaway, because it's not going to run away. It's not heating up. One of the stories going around on the internet, whoop-de-doo, is that when you connect power to a LED, its impedance drops, and if you don't control the current, it burns out. Well, it's true, the current drops, because the current's infinite if you don't have any voltage on it. When it hits a threshold, it starts to conduct, so its impedance drops until it hits a stable level. This is the stable level that this LED is running at right now. If I let it heat up, its impedance would drop, but I'm not letting it heat up, so it's going to be stable right here. And to demonstrate the threshold, I'm going to turn off the supply. The voltage will drop to the conduction point of the LED, and the filter capacitor will maintain the voltage. So that LED is not conducting anything now. That little capacitor, oops, I think I'm too close to focus, is holding the voltage. It's not discharging. When I turn it on, the voltage will go up. But the LED will take the current. Now, those transformers are rated at 1.5 amps, so I'm actually overloading it a bit. But that can be good, because that transformer can't supply too much current. And if you use a large LED and a small transformer, you can't burn it out, really. Your voltage will drop as the current goes up, and you'll hit a stable point. As far as stability goes, in case anybody thinks I'm not being accurate, I've ran this kind of LED on this kind of transformer for about 2 months now in my little indoor garden, 8 hours a day, every day, and I've yet to have a problem. Another way to power up an LED is to use a regulated supply. This one's using a 317 chip. I don't know if you can see it in here. It's well, it's mounted on that heatsink. Doesn't require a lot of parts. As you can see, I'm using 3 transformers to get the voltage I want, because I'm using whatever little transformers I had. Let's just turn that on. One of the advantages to having a regulator is I can control my voltage and my current and my brightness. It's kind of like having a dimmer. Let's set this guy up to 1.5 amps. And it's 30.4 volts. And it's quite bright. So that's 45 watts. Now with a linear regulator, you're going to lose some voltage across the chip, of course. And that's where you're going to be losing. You need about a 3 volt difference minimum. The regulator is not losing that much. If I'm losing 3 volts at 1 amp, I'd be losing 3 watts. It's not a big deal in a 45 watt supply. I'll show you what happens if you want to have a bigger transformer, but maybe your transformer is too big. You don't want to waste a lot of power on your regulator. Let's take a look at that. The transformer I have is quite a large size. It's capable of about 5 or 6 amps at 34 volts. The thing is, the unloaded voltage is going to be much higher, 44 volts. So the DC going into my regulator is going to be too high. And the 60 volts, I only want 36 to 40, so that's way too high. What I can do is use what's called a buck transformer. The buck transformer is placed into the primary of this transformer. So I have buck windings over here. This transformer is a 12 volt center tap. If I put that 12 volts in series with the primary of this transformer, I can decrease the voltage. You have to pay attention to phase, that's all. So now, instead of getting 44 volts, I should get a lot less. There's 41.7. Put the full 12 volt buck. Now I'm getting 38.8. I can just keep going. Get pretty much anything I want. DC into the regulator now. 51. So it's 9 volts or so less than I had before, which is much better. Let's power up the LED. My voltage is down. And there we go. So that's buck technology. This is my little indoor garden. Where I'm keeping my coleus over winter. As you can see, it's doing very well. got it on about a 7-hour light cycle. 7 hours, I think, of light. Either 6, 7, or 8, I can't remember. I change it every now and then. It's being ran by two Bridgelux 018. I have a constant voltage power supply up here. There's no electronics, there's no regulator. It's just transformers, bridge rectifier, and a capacitor. And I have a fan powered power supply up here, powering the fans. There's a fan on the heatsink. It's really bright. So over here. So I'm using 90 watts. And I'm using two different colors of LEDs. That's a bluish white and that's a reddish white. You can probably tell, I hope. And zoom back as far as I can be. I'll show you what I used to use to power up this garden. So this is 90 watts. And this is what I used to use. 8 T8 fluorescent tubes, 6500K I think they were. For a total power of almost 300 watts. And less than half the light I'm getting from the LEDs. So goodbye fluorescence.